Hi everyone, in this video we're going to look at some properties of logarithms, and of course with properties of logs always come exponents, and with those two things we're going to solve some equations. So let's get right to it. The first one, 2 to the 2x plus 1 equals 32. What you'll probably want to do is rewrite this as a logarithm, so we'll get right to that. This will be log base 2 of 32 is equal to 2x plus 1. And what that enables you to do is this side can be evaluated right away. If you know off the top of your head that that's 5, awesome. If you don't know off the top of your head that that's 5, what you'll probably want to do is bring up a calculator. I prefer Desmos. I use Desmos for most things. So with that said, how do you find the log in the Desmos app? Well, hit functions, over to miscellaneous. We'll do the log base function, log base 2 of 32, and it evaluates it to 5. Just as a quick reminder, we'll go over this again later, but why is this 5? Because 2 to the 5th power is 32. And again, that's another thing. If you don't remember that off the top of your head, 2 to the 5th is 32. So now that this is 5, bring down your 2x plus 1. It's a really straightforward two-step equation at this point. Subtract 1, divide by 2, and you should get x equals 2. If you aren't quite sure, as always, you can always go ahead and plug in into your original equation and get 2 to the 5th equals 32 to check your answer. So x equals 2 works out quite nicely. If you want to be fancy about it, rather than writing your answer and circling it, you can go back to set notation, and that'll be just a little more formal, especially when we get into equations with multiple solutions. All right. Let's move on to example number 2 now. We get into some logarithms. 2 logarithms with the same base, which, by the way, remember is that implied base 10. But 2 logarithms with the same base separated by a subtraction sign. We can condense those into the log base, the common log of 4 over x. If you don't remember why that is, we will debrief with these properties at the end. So log of 4 divided by x equals 2. And now, again, that implied base 10 here, since we're in a logarithm, we may want to rewrite as an exponent. We want to change fluidly back and forth between logarithms and exponents. Technically, you're exponentiating each side. You're putting a 10 to the log base 10 of 4x, 10 to this power. That's technically what happens. But what we end up getting is, oops, didn't mean to erase all that. So we've got log 4x equals 2. We've got 10 squared equals 4 over x. And so now we've got 100 equals 4 over x. Cross multiplying or multiplying both sides by x, of course, we get 100x equals 4. Dividing, and we get x equals, hopefully we can do this without a calculator, 0.04. Again, it's probably worth plugging that in just to make sure. So we'll check that out. So we'll do common log of 4 minus the common log of 0.04, and we'll get 2. So that's a nice way to verify. One last example in this section before we debrief on the properties and the ideas we just reviewed. We'll look at this one. So the first thing we got is a couple of ln's. Remember that natural log is the log base e. Right, so if we had the natural log of some number a, it would be the log base e of a. Again, we'll debrief that in a minute. But what we'll want to do here first is to condense that side of the equation. So we'll do the natural log of x minus 2. Spoiler alert, if you can condense subtraction into division, we can condense addition into multiplication. And then the other thing here is this 2 can be rewritten as an exponent up here. Again, we'll review those properties in just a minute. Now that we have a natural log of both sides, we would exponentiate each side, e to the, whatever on both sides. Effectively, that undoes the e and the ln at this point. So what we take from that is we have to multiply this guy. So hopefully we remember the distributive property. Many of you probably use the acronym FOIL to remember how to do that. But what we've got is 2x squared minus 3x minus 4x plus 6 equals x squared. Now that we know we have a quadratic to solve, we are going to think about quadratic formula. Or my favorite F word, factoring. So either way, for quadratic formula or factoring, we do need a 0 here. So we're going to subtract x squared from each side and then combine these like terms. So we've got x squared minus 7x plus 6 equals 0. Now that we have that 0, we are all set to factor x minus 6, x minus 1. Remember, we're looking for numbers that multiply. Your product is this value. Your sum is this value. That's the main factoring idea here. And then once we get to this point, x minus 6 equals 0, x minus 1 equals 0. You set both terms equal to 0 and get x equals 6 and x equals 1. So these are our answers, right? Wrong. Let's be sure to go ahead and check our answers. Why can't I make this bracket today? Specifically, let's check 1 here. What happens if I plug 1 into the original equation? Let's start there. What happens if I plug it into this part here? What happens if I plug 1 and try that out? So what we had here is 1 minus 2 is negative 1. What happens if you try to take the log of a negative number? It is undefined. We are not taking the log of a negative number is not something that's in the domain of that. So x equals 1 in this particular case is said to be extraneous. So x equals 6 is our only solution in this particular case. So in just a minute, we'll go over the important ideas of this section and debrief on how all the things we talked about so far relate to those important. So some of the important ideas that we talked about in this section. What is a log? Of course, a logarithm and an exponent. And first of all, a logarithm really is the inverse of an exponent. So we all know that 3 squared is 9. So what is the equivalent logarithmic equation of that? That would be the log base 3 of 9. The logarithm asks you to evaluate the exponent. So if we had the log base 3 of 9, what exponent must we put on top of the 3 to get to the 9? Well, that's where the 2 comes from. So fluidly coming back and forth between those two forms is definitely something you're going to want to be comfortable with, because as we saw, fluidly changing from an exponent into a log was kind of how we solved it. And then fluidly changing from a log back into an exponent was how we solved. So that's going to be an important thing to take with you. The basic structure of a log base b of some number a. And it's really important to note that a must be greater than 0. That is the whole idea of the domain. That's what caused, I didn't mean to zoom out here. That's what caused 1 to be an extraneous solution here. Sometimes the solving process, converting from one form to the other, can introduce false solutions. Usually it has something to do with squaring and that kind of thing. Making positives negative, or making negatives into a positive, that kind of thing. But that's why it's super important to check your solutions when you're dealing with logarithmic equations to make sure that domain isn't contradicted. So since 1 here made that domain contradicted, that's why it's an extraneous solution. And then the other thing we talked about, remember, when there's no explicitly written base here, it is a common log. So that would be the log base 10 of, in that case, a I wrote. And then the other common thing is the natural log, of course. The natural log of a is the log base e of a, that magical number e. Then the last couple things we talked about were the properties of logs. So the natural log of a plus the natural log of b, you can condense with multiplication, a times b. These properties, by the way, work with both natural logs and any log of any base. I mostly use natural log when I write the properties because it's fewer pen strokes, to be perfectly candid. So the log, as long as the logs match, these things work. So if we had the log base 3 of a plus the log base 3 of b, this would be the log base 3 of a times b. So the log of any base. So log of a minus log of b, as we did in earlier example, would be the log of a divided by b. So looking back, when it was subtraction, it became division. When it was addition, it became multiplication. Last property to look at, when you have a coefficient of a logarithmic expression, that coefficient can be brought up and written as an exponent, as we did in this example here. 2 natural log of x became the natural log of x squared. And so those are some of the important ideas in properties of logs, to condense, to rewrite, and to solve. So take a few minutes now and work on these check your understanding problems. I'll put the solutions up in just a minute and debrief. All right, so here's your check your understanding problems. The first one here, again, just a pretty simple conversion and then evaluating. Depending on how you're going to do it, I simply did my log base 2 of 5 to get that value. But let us not forget that in the situation, you can always graph both sides of an equation. In other words, y equals 2 to the x and y equals 5, and find the intersection of those two things. That is always a strategy you can use to solve equations. Hopefully you guys talked about that a lot in Algebra 2. Same idea in this one. For number 2, once you convert e squared equals x, you can just evaluate e squared on your calculator. Or you can graph, of course, natural log of x. Graph y equals 2. And then find their intersection point. Or, as always, you can do e squared and get that same number. So it's nice to have a couple of different approaches here. For number 4, let me just close this real quick. Same idea. Converting log base 4 of 64, evaluating to get 3. That is, of course, because 4 to the third power is 64. So remember that, and then it's just some basic algebra here. And our same strategy with graphing absolutely can apply. If you were to graph these original ones, it would be way off the map, but let me try to show you a nice quick and easy thing here. So if we plotted y equals 4 to the 2x minus 7, and then y equals 64. Let me see if this works. So you can just pinch in with these, and then again, find the intersection point to be, oh, Mr. Dodd. That was not an intentional error there. I failed to keep the subtraction symbol. I probably need to put a parenthesis up there. 2x minus 7. And now we get our x is equal to 5. That makes more sense. There you go. So last one here, we've got use the subtraction sign to condense into division. One thing to remember is the 1/2 power. 4 to the 1/2 power is equivalent to the square root of 4. Again, if you're ever unsure, 4 to the 1/2 power is the same as the square root. And then it's just a matter of inverse operations. In this particular case, I multiplied both sides by x minus 1. But you could also think about cross multiplying or whatever gets you there. All right? Let me know if you've got any questions. Talk to you soon.